Thank you, Samir. So that's the last lecture, and I wanted to make it a little bit easier again this time. But I hope not too easy given the audience. so let's see. I finally want to talk about p-adic interpolation. So if you study L values and you are able to show that they are integral under certain conditions, then it's very natural to go further and ask yourself, what is the relation between these L values? And there are very famous examples, namely the Kummer-Kubota-Leopold congruences, which show that this can indeed happen. So let me start with this motivation. Although, as I said, given the audience, this is maybe the moment too easy. But sometimes it's also nice to see again easy things because it remembers you where all these things start. So we consider the following. So we modify here C star a little bit the value of the Riemann zeta function at 1 minus k. So C is some integer. C an integer bigger than 1, and k is also integer bigger or equal to 1, and we fix a prime p, maybe I write that here, fix p prime, and C should be also co-prime to p. And then we modify the value as follows. So we take 1 minus C to the k and times 1 minus P to the k minus 1, and then times the value of the Riemann zeta function. So that's the Riemann zeta function. And so if we modify these values, then going back to Kummer and Kubota-Leopold, deeper study. So they showed the following. If k is congruent to k prime modulo p minus 1 times p to the n minus 1, p to the n, sorry, p to the n, then these modified zeta values, you have to modify them because we know that this value, this is rational, this is not an integer, so it's not so easy to talk about congruences here. So we modify them, and this modification exactly makes this integral. And you also remove somehow what is called the Euler factor at p. And if you do this, then these modified values satisfy the following congruence. This is congruent to the zeta value at 1 minus k prime modulo p to the n plus 1. Yeah? So in a certain sense, that's somehow a very surprising result, because it means that if you say two numbers are close if they are highly divisible by prime number p, that means if k and k prime are close in this sense, also the zeta values are close in this sense. Yeah? So that's something which is quite remarkable about these zeta values. And the question is how to study all these congruences conceptually. And this has been started by Kubota-Leopold, and then later, in particular Mazur, they have invented the theory of p-adic measures, which gives a very smooth way to expressing this. And I will want to recall that now. So let X be any compact, totally disconnected topological space. And the only thing at the moment which is important is you take the p-adic integers, the units in there. Yeah, the units in CP. And then we can consider the continuous functions on X with values in ZP. Yes, this is the continuous functions on X with values in ZP. And what should be a measure? I mean, everybody, you ask what a measure is. It is a linear functional on continuous function. So this is what we define. So we define the measures on X with values in ZP. That is just the ZP linear homomorphisms from X, from these continuous functions into ZP. And it is, normally you would say this function had to be continuous or something, but this is true in this case automatically. And if you have now a measure here, mu, and a function here, then we can apply, of course, the measure to the function. And as is somehow customary here in this setup for integrals, you write that like this. Yeah, that's just a symbol defining this. Okay, so that's a p-adic measure. And now, why are these relevant to study such congruences? So, so note suppose we have two functions which are continuous, and these functions differ for all values. They are congruent modulo p to the n for all elements in this topological space. Then it immediately follows that the values of these measures are also congruent. Yep. So the integral f d mu is congruent to the integral g d mu mod p to the n, because that's rather trivial. So f minus g is of the form p to the n times some function h. Yeah. So that's a clever way somehow to talk about all such congruences. And for now, in the special case where x is Cp star, these units, so if k is congruent to k prime, mod p minus 1 times p to the n, then this implies that the functions x to the k are congruent to x to the k prime if for mod p to the n plus 1, because the torsion, so because the number of elements in Zp mod p to the n plus 1 Zp star, this is exactly p minus 1 times p to the n. And this means if I take something here to this power, it will be always 1. Yeah. So so this is here for all x in for any x. This is just as a polynomial function on ZP. Yeah. So and this then would imply that if we have a measure which, if we integrate it against these polynomial functions, we get exactly back the Kummer-Kubota-Leopold congruences, and that is indeed the case. So there's the theorem by Kubota and Leopold, formulated a little bit differently. Kubota, Leopold. And it just says there exists a measure depending on this integer c, which was auxiliary, a measure on ZP star with values in ZP, such that for all k integers bigger or equal to 1, you have that the integral over ZP star of x to the k d mu c is there a question? Samir, question? Is this, you see, yeah, I mean, this is, I mean, somehow to do really abstract measure theory is I mean, in a certain sense, you say the measure is given by a linear functional on the continuous function. Yeah, I mean, it's not so easy to cook up an independent measure theory and then you prove somehow this kind of Riesz representation, but you make it a definition. Yeah, exactly. Yeah, you see, this is always a compact space here. Yeah, it has a strange topology, but never mind. And you don't take values in complex functions or reals, but you take this in this p-adix. That's number theory. But you can say what the continuous functions are, and then you define a measure to be a functional there. Yeah, and as I said, this is automatically continuous, so you don't have to worry in this setup. Yeah. So, and now the point is that there's really a measure explaining all these congruences, because there's a measure, if I integrate it against this x polynomial, x to the k, then I get exactly this modified Riemann zeta values back. Yeah. So, okay, and so if you want to study congruences, then it's much better directly to study such measures, because they yeah, I mean, there's you will see in a moment a little bit. Yeah, you will see that you can describe the measure space, the space of measures. What is this? Ah, okay. Yeah, this is in fact this is uniquely characterized, but it is somehow the point is always that if you specify the values of a measure just on these polynomial functions, that is not enough to give the measure back. You need also some relations here. Yeah. R equals to 0. K. Yeah, k to 0. I want to avoid here. Yeah. So now according somehow to the plan of this whole lecture series, let me first show you how you can get such a measure for the L values of totally real fields for the zeta functions. So measures for totally real fields. And so we are in the situation of lecture 2. And so we have again L a lattice. Yeah, L had different notations during this lecture series. And we let A now be any p-adically complete separated ring. And you can think here always, yeah, not always, but okay, you can think of ZP here. And then there's the following theorem, which, yeah, in a certain sense, maybe this is due to Amis, really. So the theorem is as follows. I need some little definition. So LP will be now always L tensor ZP, yeah, over Z. So just n copies of ZP. So then the theorem is the measures on this LP with values in ZP, in A, this is just isomorphic to the completed group ring of L, which showed up in the second lecture. So let me remind you, this was the inverse limit, completion of the group ring of L, L, modulo the augmentation ideal, K plus 1. So this is the kernel of AL to A, the augmentation. And so this means that after choosing, so this is non-canonically, so after choosing some basis, this is isomorphic to the power series ring in n variables. And you should think of this as a kind of Fourier transform. Yeah, so the measures are simply given by power series with measures with value in A are given as power series with coefficients in A. Yeah, that's surprising, and this relies somehow on Mahler's theorem. Yeah, relies on Mahler, who described the continuous functions. Yeah, so the binomials x over n. This is somehow a basis of the continuous functions. Does it really? No, I mean, no, this theorem you don't need Mahler, maybe even. I think you can go without Mahler. So Mahler's theorem would exactly give you the continuous function. The theorem continues, so moreover, so we had in lecture 2, we had this moment map, and I said I called this moment map because, so it goes now from measures LPA, because this has some relevance here in Iwasawa theory. And the moment map this to this product K bigger or equal to 0, the tensor symmetric powers of L tensor A. And now the moment map is given as follows. Now, so it maps a measure to the following. So you have here the direct sum of the multi-indices k1 plus kn equals k. And then you take the integral over LP, and you take here the functions x. Yeah, you take after choosing a basis, you have somehow, you get here polynomial functions in these variables, xn to the kn, d mu c. You integrate these polynomials, and this is the coefficient of the following element in this tensor symmetric power. So you have here somehow the basis E1, K1. Now you have to use this divided power structure here, in fact. Kn. So E1 up to En, this is the basis of L. And the x1, these are the functions corresponding to the basis. This is the dual basis. Dual basis considered as functions on LP. Okay, so and these expressions are called the moments of the measure. Yeah, this is exactly what occurs here in the one variable case. So these are the moments of the measure. And that is what is happening here with this moment map, which we could write down for any algebra. But in the case where A is a periodically complete ring, this really turns out to be just the moment map in Iwasawa theory. That's a fact where I was very surprised to see that I couldn't find it in the literature anywhere, but you can find it now in the paper together with Benze and Levy. So why is this true? The idea is as follows. So the step functions, you can consider the step functions on LP. Yeah, these are just the locally constant, compactly supported functions. So F LP to A locally constant. So, I mean, I can forget about compactly supported here, but I write it. Then, so the direct limit over all R of the step functions on LP modulo P to the R LP, yeah, this is just a finite group, and the step functions are just any functions with values in A. That is isomorphic to all step functions. So you can write them in a certain sense as a union. And that here is dense in the continuous functions on LP with values in A. Yeah. So this means, as I said, the measures are automatically continuous functions here, and then they are uniquely determined on this dense subspace. So this is dense. Here you put the soup norm, yeah? And so this implies, if you look carefully, this implies really, so the measure is the dual space here. This is determined by this. And the duals of this is just, so the dual of this, maybe I write it, the duals of the step functions, LP, this is just the dual, say the A dual here, A dual. That is just the group ring of LP mod P to the R LP. And that, as we know, the inverse limit of this gives really the measures. And on the other hand, you can also see, because this is periodically separated, periodically complete and separated, this limit here is also the same as this. Okay. Good. That's maybe just the idea here. So for the moment map, sorry, that was too early. So for the moment map, you consider the pairing. So now the dual of these tensor symmetric powers LP, where are they? Here, LA, they are just the symmetric powers, so of the dual space. So this is L tensor A dual. And so if I take here the direct sum over all k bigger or equal to 0, that's of course just the polynomial functions on this ring. Yeah, that's clear to any algebraic geometer. And now we can, of course, pair this with the measures on LP with values in A, and then we get something in A. And how does that work? Yeah, this is something. This is contained in the continuous function. So if I have some polynomial here and P, then this is mapped to mu of P. And now you have to unravel this definition I gave here in terms of the exponential map. That's a little bit of a hassle, but then you can see that if you pair both sides with a monomial of degree k, then you get the same value, and then you get it. Please. No. Which primes were inverted yesterday? All primes I had inverted? Yeah. But I mean, yeah. But you see here also, at the moment, there's nothing inverted. I talk about measures. Yeah. So measures for prime. Yeah. But then if you look here was a little condition. Yeah. Which I write again. So to make this integral, so what you have to suppose is that C and P are co-prime here. So that means if I'm in a ring where C is maybe inverted, I can still look at the prime P. Yeah. So if I'm in the ring Z1 over C, yeah, so I can somehow localize at P and I have no problem. Yeah? Here, of course, there's no C because this is a general measure. Yeah. So, sorry, I wrote C because I had C here. This was just an oversight. Sorry. Here, this is for general measure. No C. Sorry. Yeah. This is divided power notation. Yeah, because the tensor symmetric algebra, this is a divided power algebra. So this means just you take E1 to the tensor K1 with itself. Yeah, that's a symmetric tensor, but this is not the K1th power in the tensor symmetric algebra. Yeah, there is this relation. So e to the tensor K, that is e to the K divided by K factorial. Yeah, so that is the divided power structure of the tensor. This is the divided power ring. Whenever you have a free module, then the divided power algebra is just the tensor symmetric algebra. Yeah. Good. Okay. So that was some recollection about these measures. And now let me let us go back to the situation for totally real fields. So again, we have some field degree n. So f was totally real. And what else do we want? We fix a prime number. Fix p prime number. And we also needed certain ideals. So C, this was an auxiliary ideal which takes the role of this little c, which I just erased. And then we have F, which plays the role of the conductor, and B, which plays the role of the ray class group. So that's auxiliary. That will be somehow the conductor of, and that will be the ray class. And they should be all ideals in OF, and they should be co-prime to each other, co-prime and co-prime to. And C and C has to be co-prime to. C has to be co-prime to P. And then our lattice L, as in the second lecture, so we take this ideal F times B inverse. That's our lattice. And we take the torsion points. This is C inverse times L divided by L. So these are the C torsion points in the associated torus. Here. Okay. Now for some function a d 0 gamma with values in d, yeah, which so these are supported on the torsion points. The values sum up to 0, and they are invariant anti-gamma. So gamma is now the, say, positive 1 units mod f. For such an alpha, we had this class in the torus TL, so that was TL minus D, gamma equivariant, with values in this logarithm sheaf. And so if we now have some, consider here, so L tensor R, that is this L tensor R, this is of course just F tensor R, real vector space. So we have 1 in here, and that is an F torsion point. And we pull back this class along this F torsion point. Yeah. And then we get somehow just a group cohomology class of this group gamma with values in 1 upper star log. And this can be mapped, 1 upper star log, by the F multiplication. This can be mapped to n gamma. Now the A completed group ring of L. Yeah. So, and that's just the measure space. So what we get is something in H1 n-1 values of the measures of LP values in A. And now we do exactly what we did by evaluating the things yesterday. So we take a cap product with some generators. So of course we assume now that this is torsion free here. That's always torsion free. That's fine. In the real case, it's always a little bit simpler to get something torsion free. So then we take the cap product with a generator of the homology of gamma with values in A, say, gives then a class, gives, so maybe I give it a name, generator eta. So it gives, we have 1 upper star for alpha cap eta, and this is now a measure in the co-invariants under gamma. And these are the gamma co-invariants. So, whoops, we have constructed a measure. Yeah? So, you see, we didn't do anything. Yeah? The measure was simply given to us just because in the case of a p-adically complete ring, this is just Sieber-Saba algebra. So, it's just the space of measures. Yeah? Nothing, I mean, really, there was no work. Yeah? Now we have a measure. And now I explain you that with no work, we see what the moments of this measure are. Okay, let me show this. So consider now the commutative diagram. As follows. So we consider the ring, say, Z, and we invert the norm of that ideal C. Yeah? That's our A. And so then, if we take now the completed group ring for this L, and take the gamma co-invariants, then we had the moment map. This existed also for any ring. Yeah. So this goes to this. So this just records the moments of this measure. T-sim-k L tensor Z 1 over norm C. And here you have to take also gamma co-invariants. Yeah, they don't matter so much. But, sorry? Yeah. Sorry, the A, sorry, you're right. At the moment, that's now, that's bad. So A is not bad. A will be the localization at P of this. Sorry. Yeah, thank you for pointing that out. I was now back in the notation of lecture 2. There was a arbitrary. So let's consider this ring. Yeah, for this ring, that's a situation. We computed these moments. Or I gave the computation here of these moments in lecture 2. So you can get it by going to the complex numbers, and then you can express these values in terms of certain regularized zeta values. Yeah, I recall the formula in a second, but this was computed in lecture 2. Yeah, and now we can do the following. So we consider the localization at P. So because P is co-prime to C, we have a map to ZP. Yeah. And this gives us now, if we go to ZP, this here becomes the Iwasawa algebra. So this is the measure space. Measures on LP with values in ZP, gamma co-invariants. And here we have also the moment maps. And this moment map now describes us the moment of these measures. And it goes the same thing. Moment map was completely functorial and everything. So we just land in the measures, the moments of this gamma co-invariance, and this is commutative. So what does that mean? So we have not only constructed a measure, we have also computed the moments. Yeah. So what do we get? Yeah, there was, not a single computation needed. Yeah, so it's just functoriality, just a commutative diagram. And let me see, I started. Yeah, I have plenty of time. I will maybe finish a little bit earlier. So we get the following theorem, which was originally proved by Deligne and Ribet in a famous paper, and independently also by Castelnugues and Barsky. And it says the following: there exists a measure mu C, F such that the kth moment, I write down, is norm of C times the zeta value 1 F times B inverse evaluated at minus K, which was defined in lecture 2, minus zeta 1 C inverse times F times B inverse at the value minus K. Yeah, these are regularized zeta functions. Yeah. And these are up to a normalization, so I think they came out with a factor norm C to the power minus K here, but that's all unimportant because norm of C is invertible here in any case. So we get somehow this result back. Yeah, and maybe I should remark so that the original theorem of Deligne and Ribet, Castelnugues and Barsky used a little bit different methods, but Deligne Ribet relies on the arithmetic moduli space. Arithmetic moduli space of Hilbert abelian variety of abelian varieties with real multiplication. So it's a little bit like the theory of Shimura. But they needed even a refinement. So to get at the integrality, they needed to have integral models for this moduli space. Yeah, so we avoid all that. I mean, this is, as I said, it's just the topological construction with a little bit of very classical and stupid cohomology, and we get that measure somehow for free. Please. There's no ordinarity here for totally real fields. That comes now. Yeah, because for totally real fields, we have for NEP these measures. Okay. Okay, thank you. So this is exactly the next point of my talk here. Now we want to do the same for totally complex fields. And so it will be essentially as easy as that. Yeah. So 3 measures for Hecke L values, totally complex fields. Yeah, so we want to interpolate now these partial L values, L chi 0 with this ray class, divided by some periods, omega alpha times omega dual beta. So if chi has the right, if chi has infinity type beta minus alpha. And so recall the setup here from yesterday. So we had A over K, an abelian variety with complex multiplication by OL. So I'm sorry that there are now too many L's on the board, but somehow that the one paper uses this L, the other paper uses this L. And as I said, I want to stick to the notation there to make it easier to compare. So L is now this totally complex number field, yeah? And so of type CM type sigma, and L over Q, that is degree 2D, and L contains a CM field. Okay, and then we had also the completed Poincaré bundle. Completed Poincaré bundle. Okay. So now we have to talk a little bit more about measures. Because we need now a more geometric perspective. Yeah, this here was a perspective about group algebras or Iwasawa algebras. And now we need a more geometric perspective on measures. And this goes as follows. So measures again. So to keep things simple, I just work with CP. So this is, you take the algebraic closure of QP and complete it, and the integers in this ring is OCP. And then we know, because this is p-adically complete and separated, so the OCP, the completed group algebra, these were the measures, yeah, on LP, now with values in OCP. So, but now Nick Katz has somehow observed the following geometric interpretation of that. So if you take the formal spectrum of this ring, here's OCPL, yeah, that's some power series ring. And it has even a Hopf algebra structure because it's a completed group ring. So what it gives you is you get the formal completion of the multiplicative group tensor the dual lattice L. Yeah, so L is just the dual lattice. Yeah, this means choosing a basis here, you get simply n copies of the formal multiplicative group. So this implies that the measures LP with values in OCP are just the global functions of this formal variety. Yeah. Yeah, that's now again another kind of Fourier transform somehow. So if we have a function on the formal torus, we get a measure. So now the idea, once you see this, is of course, can we cook up with the class we had yesterday, maybe a function here? And that's indeed the case. So fix now a prime P, which does not divide the discriminant, P prime number, prime. And as always, you have to fix some embedding of QP into bar into CP. And in fact, also, this will not show up really. Q bar maybe into C. Yeah, that's not so important. But now comes the ordinary condition. We need that prime to be ordinary for A. Yeah, so such that A and A dual are ordinary at P. And you can say this as follows. Each prime ideal in K plus, in K, so K was a CM field, and K plus is a totally real subfield of which this is a quadratic extension. So it is, I'm sorry? At identity, exactly. Yeah. Maximal real subfield. Each such prime ideal above P splits completely in K. So, and what that gives us, this implies that the formal completion of the abelian scheme A, this is isomorphic to the formal completion of GM to the d power. And the same is true for the dual abelian variety. Yeah? So there are not too many, there are infinitely many ordinary primes, but somehow there are many other primes, and with this method you don't get immediately something, but in a preprint I hope to, which will come out soon, Johannes Sprang and I also construct certain p-adic L functions for non-ordinary primes, but today I will not talk about that. So we can arrange to make this a little bit more canonical. Arrange that a hat dual is isomorphic to GM hat tensor OL tensor ZP, yeah, over Z, say, or over ZP. So that is such that this is compatible with the OL action. With the OL action on both sides. And now these isomorphisms here, they allow us to define also p-adic periods. So we can define omega p, which is an element in O Cp to the power sigma, and we can define omega p dual, which is an element in O Cp sigma bar. These are p-adic periods. And this is such that we had this basis omega A, yeah, omega A, which consisted of the omega A sigma. And these were differential forms on the abelian variety. And you have them also on the formal completion. Yeah? And then, on the other hand, on GM, you have the canonical differential. Yeah? So omega, I just write omega GM hat to the power D. And these two compare with this period. And here, this is, you have a canonical differential on this, which is just T dt dt. Sorry, what do I want to say? Dt divided by t. So, yeah, that's the canonical differential here. So now, via this isomorphism, you have two differentials, and you compare them, and you get the periods. And similarly, for the dual abelian variety. Of course, you have to be a little bit careful here with these choices, but I don't want to go into this because that's now very technical. And now we have set up the stage, and so we can now. So now comes the most important theorem here. So because we want to produce classes there, and that's the following theorem. So we do the following. So we have so the p hat. This is on A. Yeah, this was the completed Poincaré bundle. And we restrict to the formal group A hat. This we can do. And then we look, what are the global sections here for this restriction? And it turns out that over this formal completion, this Poincaré bundle is in fact trivialized. So that's the same as the global sections of just the structure sheaf. Yeah, and now with this isomorphism, this gives us something in a function in GM hat tensor OL tensor ZP over ZP, and that will give us just a measure on LP with values in OCP. That's so why is this the case? This a similar idea has been used by Norman in his study of p-adic theta functions, but somehow from the setup we have been doing, it's very natural that this is the case. I mean, of course, formally the Poincaré bundle, because it is the universal bundle and there are non-trivial deformations of line bundles, you would not expect that it becomes trivial if you restrict just to some formal fiber here. Yeah. So in general, that's not trivial, but here it's happening because of the ordinarity condition, and maybe very, very roughly the idea. It's not difficult though. Yeah. So this is the formal group associated to the p-divisible group. A p sigma infinity. Yeah, now I have problems in notation. So p sigma are somehow the product of all the primes p which are induced. So p is induced by the embeddings of sigma into and then also via the chosen embedding iota p of qp bar into qp. What did I wrote? Did I wrote qp here? I wanted to choose this. Q into cp. Yeah, this gives you, of course, each embedding here of L into this, composed with this, gives you certain primes, and these I collect, and this gives us a big isogeny. So I some isogeny on the abelian variety. I take the p-divisible group, and I can do the same with sigma bar. So then multiplication by this p sigma is étal with étal dual. And if this is the case, this formal Poincaré bundle is isomorphic. So this implies that the formal Poincaré bundle is isomorphic to, if I pull it back along this isogeny, and this implies that it is trivial on these torsion points, and you do this now for all powers n, and then you're done, and similarly for the dual. Okay. So now we want to construct this this measure or this function giving the measure. I erase it, but that here we want to be n. And that's now easy, because we have a class with values in this completed Poincaré bundle, and we just have to evaluate it on the formal completion of A. So, now for rho, some function in the C torsion of the abelian variety, 0 gamma, where gamma is, as before, this the 1 units mod f. F was this ideal, and we have x. X is an F torsion point on A without C, F torsion. We want now to have some measure, which I call the Eisenstein measure, associated to rho and x in the global functions of this formal completions, which were just the measures on LP with values in OC. So how to do that? So, and this should have the right moments, of course. Yeah. Correct moments. So how do we do that? So we consider, the problem is we have taken away the 0 point. So we cannot somehow take the completion at the 0 point, yeah, of our class. And but that will not turn out to be such a big problem because we translate that point back. So this here is this is the formal completion of A at this section X, and we let tau of X be the translation action, so Y goes to X plus Y, and then we have the following diagram. We had this Eisenstein-Kronecker class, gamma A rho X, and this was in HD minus 1 gamma of sorry, I don't want to have X here, rho. A minus the C torsion points, gamma, and then you have this P hat, tensor omega d. And now we do the following. We use the translation action. So I do the following. I translate this class via x to the zero section. So I translate the whole situation, and then I can really restrict this to the formal completion at 0, or the identity. And then I get something in h d minus 1 a hat gamma, and here I have to restrict the translated Poincaré bundle. So the translated Poincaré bundle, I map Tx upper star p hat. I map to so if I evaluate that at E, sorry, I want to say that this has a map to p hat yeah. So restrict this to a hat. This has a map to this, which is essentially given. So because this is an f torsion point, this is given by f multiplication. And this I use also. So I pull back this class, which means I can evaluate now at 0, and then I map. I have to pull back along this translation, the Poincaré bundle, and then I can evaluate also at 0. And this has a map to this by this isogeny. And then I use the trivialization of the Poincaré bundle I had over there. Yeah. And if I do all that, then I get something here, HD a hat. So p hat restricted to a hat tensor omega d. And because now this is affine, this is just group cohomology again. And so we get something, together with this trivialization, we get something in H0 a hat times a hat with values in the structure sheaf, which were the measures, so tensor omega d. With the given basis we had, we can also trivialize this. Yes, so this trivializes with the basis omega a. So we can forget about that, and this is then just the measures on LP with values in OCP. And you have to take again the gamma coinvariance. Sorry, there's again a map cap product HD minus 1 gamma with OCP with some generator here, and then you go to the measures. Yeah, so this class gives us then the measure we want, rho x, and here again we have that moment map, and exactly, which goes to the that's now a little bit, yeah, okay, I write it not with all its decompositions here from my lecture yesterday. So that's OCP, gamma coinvariance. Yeah, I only want to say that with the same trick as we have used for totally real fields, we have computed the moments over the complex numbers, and because the moment map is functorial, we know the moments everywhere where we have the moment map. Yeah, and so we have a measure here, and the moments are exactly the moments we have. Sorry. Are there some a dual missing here? This is what you mean? Yeah. Thank you. Here also. Thanks. Okay, so we end up with the following theorem, and that will be my last board. So somehow with this geometric interpretation of measures, we get directly a measure, and then we can generalize earlier work of Nick Katz. So theorem, so this Katz for L equals CM field, and myself and Sprung in general. It's as follows. So there exists a measure i's rho x measure on LP with values in OCP gamma coinvariance, such that the following interpolation formula holds. So if you divide here by the p-adic periods to the right powers, alpha plus 1 sigma times omega p dual to the beta, here you have now the integral over LP of T and S are just some variables, yeah, alpha, beta, and now d mu Eisenstein rho x. That is equal to, we have some factors, -1 d times d minus 1/2 and alpha factorial. I hope the sign is correct, but we checked it really several times. Signs are always difficult in this game. So this runs now over all C torsion points. Lambda, this was the period lattice, yeah, lambda period lattice, as we had yesterday. And now we have here rho minus T. And now we have these Eisenstein series I defined also yesterday, beta alpha plus 1 over S, T plus X, comma 0, comma lambda, comma gamma, and here you divide by the complex periods. Yeah, so alpha plus 1 sigma beta dual. Yeah. Okay. And with this theorem, I would like to end my lecture today. Thank you very much. With the integral, here there's sorry. So this is somehow you choose. These are the moments, yes? So T and S are variables. T and S are variables. So LP on LP tensor OCP, which somehow can be written as something like OCP sigma plus OCP sigma bar. Sorry, this variables, yeah? So these are somehow multivariables, and you have a sigma part and a sigma bar part. So in total, you have really 2D variables here, yeah. And so these are the moments, but these are multi-indices, yeah. So these are multivariables, yeah. sorry, this I should have explained. Thank you for asking this. Yeah, you see, yeah, exactly. That's a good question. There's a need for OCP here, and you see the need is these p-adic periods. They don't live in ZP. They didn't show up in Kubota-Leopold and also for the totally real field. The periods for totally real fields, they are very easy. They are just 2 pi i's and powers. Yeah? And there are essentially, so the p-adic periods are not there. Yeah? That's a special feature. But here you need p-adic periods, and they can be defined over a slightly smaller ring. But it doesn't help so much to make that ring more precise, because in the end, this doesn't give you any additional information, because you know already the integrality of these values and where they live. Yeah, so to have a measure, you can be generous with the coefficients. Thank you. More questions, please. What can be interpolated? Yeah, I mean, this is for all alpha and beta. Yeah, I mean, this interpolates for all alpha and beta. So you get all infinity types of these characters. Yeah. So somehow you have this t and s. These are multivariables. Yeah, and for each of these multivariable, they are determined. So the monomials determine you an infinity type of the Hecke character. Yeah, and if you use this integration formula, I mean, you get first the Eisenstein series. I mean, I could have given you also the final outcome. So if you want to relate this to the L value, then you have to choose here the right row, and you have to be a little bit careful with characters and so on. But that's quite technical, because to formulate that properly, you don't work on LP, but you want to have a measure on the Galois group. Yeah, and that's a lot of work to do, really, and many notations. But as we have discussed that these are essentially the same as the L values, I just give you the theorem like this. Yeah, but it interpolates for all infinity types. This doesn't make any sense here. No, because there are no reals here. This is p-adic. Yeah, p-adic. P-adics are stupid. They have no ordering. This is a field only for number theorists, not for analysts. That's stupid. Sorry, how I did get it? The uniqueness. Such a measure, if you have a measure, it's uniquely determined by its moments. Yeah. That's also unique. Yeah. Yeah, but you see, any natural infinite subset of the natural numbers is already dense in ZP. Yeah. So if you have something continuous on that, it's unique. Yeah. So I mean, you can even specify it on much less. Yeah. Thank you. Yeah, I would like to thank for the nice hospitality, especially once again Samir, who did a fantastic job in organizing everything, and of course the lecture the people who somehow attended till the very end. It was a great pleasure meeting you all. Thank you.